Hello there. The topic for this video is what is it? Polarization. Uh, yes, this is polarization. Polarization is nothing but dipole moment per unit volume. If you've understood this page, this slide, then you should be ready for the next one. Yes. So how colorful. So now we'll be finding how to find electric field due to some polarized object at some point whose position vector is r bar. Now, what is a polarized object? A polarized object has many small dipole moments within it. The green color, whatever you see here, the green color ones. So, the electric field due to this polarized object is nothing but the electric field due to all of these small dipoles. I have to find the electric field due to all of these small dipoles at this point r bar. I know that if there is only one dipole, I can apply this formula, but then and this is valid for large R. But here there are many small dipoles here, so some integration will be involved in this. So if there is any small dipole moment, let's say some dp bar, it can be written as polarization into the volume because I know polarization is dipole moment per volume. So if I multiply this with the volume, I'll get my uh, dipole moment. And yes, a bit about the convention that we use in class, wherever there is dash, like r dash bar, r prime, yes, prime variables, prime coordinates, it represents that the variable is like, it's inside this, it represents anything that is within this region of this polarized object. If it is outside, then I can use normal variables. That is one convention, one form of convention. Because dipole moment is zero outside. There are no dipoles outside the region of this polarized object. So, anyways, so the potential. How do you find electric? I mean, if you find the potential, you'll be able to find electric field as well. That is not a problem. So the potential due to, I mean, I can change this now. What's the big deal in that? Oh yes, we are good to go. Anyways, so yes, there's no mistake over there. Potential due to a polarized object at some r bar. This equation is very similar to this equation, which is nothing but the potential due to a small dipole moment p bar at r bar. P bar is like integration of all of this. If I integrate this, if I integrate dp bar, I will get my p bar, which I've written it here, integral p d tau, and the dipole moment formula will still apply here. It's here. The color is in pink because it is representing this arrow. That is what I mean here. And blue arrow is this one, red is this one. So that should help. Because if you look at the old formula, here R is nothing but the distance between the dipole and the point of interest, whatever it is. So the pink vector, R bar minus R prime bar, that is the vector that is uh, joining the dipole moment and the point of interest. That's why I colored this in pink so that there is much clarity over there. After some simplification, you will get this formula. I can represent uh, potential due to some polarized object in terms of this one, this summation. So we've introduced two new variables here. One is sigma b, two new functions you could say. Sigma b and rho b. Sigma b is nothing but the bound surface charge density, and rho b is nothing but bound volume charge density. You could look at the derivation yourself, that is none of our concern. And yes, during the derivation, we used this one, the second one primarily. You might get confused. Why is there no minus sign here? Because uh, the thing is we are finding the gradient with respect to the primed coordinates. So that's why there's no minus sign. You could look up the derivation yourself, but these two are different things. There is no prime coordinate here. There is a prime coordinate here. This is used in the derivation. So, anyways, uh, so sigma b is given by this one, and rho b is given by this one. Nothing much left here. Everything is covered. So, if you know polarizability, this is polarization. My bad. If you know polarization, you can just solve this problem. It is very easy. So what is this bound surface charge density? Is nothing but the charge accumulated across the along the surface, whatever it is, on the surface of this polarizable object, and the volume charge density will tell you what is the volume charge density within this material, inside the material. Now, what do I mean by bound charges? Bound charges means they can't, they're not free. Opposed to free charges, which can move anywhere, bound charges can't move anywhere. They are there because of some reason. Let's see an example. Let's say I have three randomly aligned dipoles. The moment I apply an external electric field, all the dipoles, all these three dipoles are going to align along this external electric field. Now, these dipoles have no choice. Before this electric field came into their lives, they were living happily. They're very random. They have their own choice. I mean, not that they have conscience or something, but then they're randomly living their life. But when I apply external electric field, they're all there. So they're bound here. They cannot move. They're not free charges. Whatever charges are there on the dipole, they cannot move. They are bound. So that is where the concept of bound charges come in. I mean, plus minus, they will negate each other. So finally, it looks as though there is some long dipole or whatever, some long thing over there with bound charges on the either ends of this line. You could consider this as a long dipole, maybe. Yes, a long dipole. This minus charge and this plus charge can't go anywhere because of this externally applied electric field. They're bound to be there. They're not free. They're prisoners of this electric field. Anyways, so now we'll try looking at the interpretation. We got this formula in the beginning. After simplification, we got that sigma b is nothing but polarization dot n cap. N cap is the normal vector, the vector that is perpendicular to the surface. So if you take an example, if you take some polarized tube, which is very similar to this one, or long dipole, whatever, it's very similar. See, that's what I wrote here. It's very similar. So if I take a small chunk of this tube, it's going to represent one of those dipoles. So I just took a small chunk of it, whose area of cross section is A and length is D. I mean, now let me try to find the dipole moment of this chunk. How do I find it? It's just this one into its volume, and I know the dipole moment is nothing but the charge into the distance. Now, what is the charge here? Whatever charge is on the surface, this area of cross section, the side ones. Let's say it's QB. It's bound. It is bound because it's a polarized tube. You find bound charges there. So if I compare these two equations, finally I'll get that the Q bound is nothing but area into polarization. Sigma b is nothing but Q bound by area. You'll get polarization. But this is a very special case. Everything is very perpendicular. What if things are not perpendicular? What if your area is like this? Area of cross section is like this, but your polarization is in some other direction. So, how do we find it? By definition, sigma b is nothing but your bound charge by area. So, here the new area is a dash. This prime is not related to anything. It's just a new, not related to the not related to this prime. These primes are different. The primes in red color. I just have a new variable here. That is why I chose prime here. So QV by A prime. How do I know A prime? A prime is nothing but A by cos theta. Some trigonometry you do, you get this relation. So finally you'll get P bar dot n cap. There is nothing much here. What is more interesting is the next result. This is very interesting. When I say volume charge density is minus of uh, divergence of P bar, what does it mean? If P bar is positive, if this is positive, that means uh, positive charges form on the surface. I mean, that is very much obvious. If you have positive divergence, it means things are going from inside to outside. All the dipole. What is P? P is dipole moment per unit volume. If divergence of P is positive, it means all my dipole moments are pointing outwards, which is here given in the diagram. So the tip, this arrow mark represents positive charge. So I'll have positive charges on my surface of this polarized material. If that is the case, all the negative charges at the tails of these dipole moments, they will be inside the material. So that is what I've written here. Negative bound charges form inside the material. Bound because polarized. And if all the negative charges are inside the polarized material, what does it mean? The volume charge density is negative because you have negative charges inside. And that is the same thing what this equation is telling us. If divergence of P is positive, negative of positive is negative. So my volume charge density is negative. If divergence of P is negative, that means my positive charges are inside and negative charges are outside. That means negative of negative will be positive. My volume charge density will be positive. That is obvious. If all the positive charges are inside, it means the volume charge density is positive. That is the interpretation. So this is an interesting result. So if all these positive charges are outside, it means an equal and opposite charge, equal and opposite quantity of charges inside the material, because it was initially a neutral polarizable material. Due to some externally applied electric field or whatever, it became a polarized material, but total net charge is zero. So whatever charge goes outside, the same charge is also inside, but with a negative sign, because if positive is outside, negative will be inside. If negative is outside, positive is inside. So magnitude is same, but the sign is different. So if I have a very small bound charge on the surface, or no, in the surface, it will be the negative of whatever is outside. Sigma b into dA will give me uh, a small bound charge that is outside on the surface. Negative of that will give me uh, the charge that is inside the material. So we know what is sigma b. It is p bar dot n cap. You do all this simplification. Finally, you'll get the same thing. What theorem did I apply here? Some theorem. Gauss divergence theorem. Yes, you'll get the same answer. If you want me to tell this again, it's nothing. Whatever charge is forming on the outside, uh, equal and opposite uh, charge of the same magnitude but opposite in sign will be inside. So since it's a neutral material, this is the fact. Net charge should be zero. So whatever is outside will also be inside, but both of them will have opposite charges. That is why this minus sign came here. Sigma b is nothing but bound charge on the outside per unit area. So if I multiply with its area, I will get bound charge on the outside. So bound charge inside is the negative of bound charge on the outside. That is the meaning of this equation. So everything that follows will finally lead to this equation. Yes. Do we have anything else? No. This is polarization. This result is interesting in particular. I don't see any interpretation in this slide. Bound charges. Yes, this is the important thing. This thing in the box. Polarization. Yes, that's it. There is nothing left in this video. So thank you for